let's look at geometric distribution. Okay? Let's got a little definition of the formula for geometric distribution. Let x, okay, so x be the random variable equal to the number, so what this stands for, the number of trials required before a success. Okay, and we'll talk about what types of questions would be worded this specific way, because it seems kind of odd the way they've written this. And they're telling you that the probability of wait time before success is equal to what they call q to the power of x times p. P is the probability of being successful, okay, so that's when it's great, and then q, and I just kind of wrote in, is the probability of failure, so not being successful. So the idea is, what's the probability, let's say, that I'm successful on the 100th trial? Well, that means I'd have the probability of failure, whatever it is, to the power of 100 times the probability of success on that 100th trial. Okay, so that's how we calculate it. So let's go into our question here, and we'll separate it into two different questions. Number one, for a 12-sided die, what is the probability that the first 10 will be on the 2nd, 5th, and 10th roll? 5th, and so these are all separate questions. I should have kind of written like this: A, B, and C for all of them. Right? We're just going to go through three different questions. So for the first question, we'll read it again. For a 12-sided die, so what that means is there's 12 options. Okay, what's the probability that a 10? It doesn't matter what number they've given us. This is kind of irrelevant information. It's that it lands on one specific side. Will be on the 2nd roll. What's the probability to be on the 5th roll? What's probably on the 10th roll? So according to our probability here, okay, so probability of x, right? We said x was going to be success on the 2nd roll, right? So we're looking at what's the probability of failure to the power of 2. And actually, because it's on our 2nd roll, what that means is, in terms of counting, we're going to have one failure. So that's going to go to the power of 1. And then on our 2nd attempt, we're going to have our probability of success. Okay, so we've got to figure out our probabilities. Probability of success, well, it's a 12-sided die, and it's landing on the side with the number 10, which means we have a 1 in 12 shot, assuming, you know, it's numbered 1 to 12, right? So our probability of success is 1 in 12, which means our probability of failure is 11 in 12, yeah. So when we go to write this out, 11 and 12 to the power of, well, it only occurs once, so anything to the power of 1 doesn't change that number. And then we got to multiply it by 1 over 12, which means we're going to get an 11 in 144 chance. So if we wanted to convert it to a percentage, we bring out our lovely calculator. Okay, so we have 11 divided 144, and you have a 7.63, so roughly 7.63 approximately % chance that you'll get the 10 on the 2nd roll. Okay, so with that being said, let's talk about the 5th roll if we were to set that up. Very, very similar question, so I'm going to steal the information. The setup is the same, the 11 over 12, and then our probability of success is 1 over 12. But this time our exponent, because it's on the 5th trial, that means this would be number 5. So that means there are 4 trials before that. So we have to put this one to the value, or to the power of 4 first, and then multiply through. So we'll do that on our calculator here. We're looking at bracket 11 divided by 12 to the power of 4 times, I hope this is going to do this in the right order. Oops. I'm going to do an extra bracket around it just because I'm unsure of how they'll set this up. 11 divided by 12 to the power of 4. So all of that in brackets. In BedMass, I want that to happen first. And then multiplied by 1 over 12. Okay, and this will give us our percentage. And the percentage likelihood of this event happening is 5.8. Approximately 5.8, so not much less, right? 5.8%. The idea of happening in 2 was 7, and then we added another 3 trials before, and the probability only dropped by like 2%. So with that being said, what about on the 10th trial, right? 11 out of 12. Because it's on the 10th trial that we're successful, we want this number to be to the power of 9. Okay, and again, we can plug into our calculator. In fact, I'm pretty lucky I can do this, and I'm just going to change the exponent to the number 10. And we're down to 3.49, so approximately 3.5% chance. So again, it's it goes down really steeply at first. You'd almost think of it if you were to draw it in a graph, okay? If we were to draw like a graph, because geometric is like exponential type relationships. You'd have something like this where the probability drops really quickly in the first couple trials and then really starts to level out later on. You can tell it's not dropping by much, and we're jumping up by quite a few numbers, right? We went from 2 to 5 to 10. From 2 to 10, there's only a 4% drop, right? So pretty unlikely there. Okay, and then the last one, expected wait time. Okay, for expected wait time, your formula is equal to the probability of failure over the probability of success. So, what's the expected wait time until a 1 is rolled? Well, the probabilities are the exact same, whether the number is 1, 10, 12, okay? Because you're choosing one side of a 12-sided die, the probabilities don't change. So, let's do this one in black. The probability of getting a 1 is, say, 1 in 12. And the probability of not getting a 1 is 11 in 12, right? Everything else is not a 1. So we got to remember our division rules. Q is on top, so you have 11 divided by 12, all divided by 1 over 12. So this is division of fractions, which can be really confusing when written this way. So it's actually easier if we write it kind of like back when we were in elementary school. 11 over 12 divided by 1 over 12. And when we divide fractions, there's a little trick where they tell you to multiply the question and invert. So they say to invert and multiply. So we have 11 over 12 times 12 over 1 is equal to, and on the bottom we'll get 12. And 11 times 12, I think it's going to be 132. I think that's it. I'm going to double check here. 11 by 12. 132 divided by 12. Great, so we get 132 divided by 12, and that's equal to the number 11. Okay, so we expect to wait 11 rolls before we reach the number 1. So on the 12th roll, we expect to reach number 1, and that kind of makes sense. You have a 1 in 12 chance. So by the 12th roll, you would expect it to have reached a 1. You should have reached it by that time. And that's what they mean by wait time.